Hi, this is Dr. John Bergduff. In this video, we're going to explore set operations and their properties. Particularly, we're going to be looking at unions, intersections, and complements. And I'm going to do this using what we call in education manipulatives. Manipulatives are basically objects that you can handle and touch to explore an abstract concept in a kinesthetic way. Putting it very simply, manipulatives are toys, but toys that help teach you something. And I'm going to use some toys to explore some of the ideas of set operations. What I have in front of me is a collection of buttons. Some of them are square, some of them are round, some of them have 2 holes, some of them have 4 holes, some of them are yellow, some of them are black, and some of them I'm going to call this color gray. I know that's not really fair. It's just sort of a dark yellow, but we'll call it gray for our purposes. So I want to explore ideas of sets by creating a Venn diagram that has a set as part of a universal set and placing the buttons on the set on the diagram in a way to illustrate different things. So we have a little worksheet we're going to work through here, and there's some reminders of things. We remind ourselves that a set is a collection of objects called its elements or members, and sets are usually denoted by capital letters. This symbol, I'll write a little bit bigger, represents is an element of, and if you put a line through it, that means not an element of. A universal set is the collection of all objects that could be used as elements of sets in a given situation. And the universal set is usually denoted by a U. You see that here in this illustration of the Venn diagram I have in larger form over here. So I have, there's 2 Venn diagrams. I'm going to bring another one up in a minute. I want to take this one, and I'm going to put those in a certain way. So I would like A to be the set of all the round buttons. I'm going to take all the round buttons and put them in set A like this. All the round buttons go in A like this. And notice, by the way, that all these buttons have 2 numbers on them. There's a number across the top that on all of them says 2.1.1. Don't worry about that. That comes from the book from which I got these. But they also are numbered to, there's 8 and 7 and so forth. Now, we want all of the buttons to be somewhere on this diagram. So if A are the round buttons, then the square buttons have to be outside of A, out here in the universal set. This is going to illustrate for us the idea of complement. Try to get them all on there somewhere. Okay, there they all are. So we write this set. We write sets in set braces. Our first question, we're going to say, when the elements of a set are listed, they are usually listed within set braces. For example, the set Francis, Tobias, Barnabas, Samson, the set of some of my cats, not all of them. Using this convention, list by number all the elements of A. So A are these buttons in here. Let me pull them all out. We have the button 2, 7, 1, 14, I'm labeling them by their numbers, 10, 4, and now I can see the last 2, 11 and 8. You might remember from previously that the order of the elements in a set does not matter. We may be, if we're sort of a little obsessive compulsive, we might want to rewrite those in order, but that's not really necessary. The order doesn't matter. That's all the round buttons. Now we want to list by number the buttons that are in U but are not in A. That would be all these square buttons out here. Let's list them. So I think we can see these a little bit more clearly, especially if I turn them up right side. We have 3, we have 5, we have 6, 9, 13, 12, and 15. So again, that's 3, 5, 6, 9, 11. Am I right? 9, where did 11 go? 9. No, there's no 11. 3, 5, 6, 9, 12, and 13. 3, 5, 6, 9, 12, 13, and 15. Forgot about 15. And notice that I just can't help myself. Teachers are all slightly obsessive compulsive, and so I put those in order. So that gives me the idea of what we're going to call complements. The complement of a set, denoted by taking the name of the set and putting a bar across the top, is the set of all the elements in the universal set that are not elements of A. Now we're going to take all the buttons off of the Venn diagram and start over. Let A be the set of round black buttons. Round black buttons. That is only these 3 that I can see. And if the other buttons have to be here, then they've got to be out here somewhere in this outer darkness. Outside of A, but still in the universal set. We'll just get them all up there. So it would look like that. And we're going to be first of all, we're going to ask to list the elements of A. We see those there in the center of set A, 4, 11, and 14. The complement of A would be all the elements that are in the universal set, but not in the set A. That would be all the remaining buttons. Let me pull them off just so I can see them clearly. We would have 10 and 13 and 6 and 2 and 1 and 3 and 5 and 8 and 9, 7, 12, and 15. That's all of them. I'll put them all back so it looks right. And I'm writing that in set braces like that, so I can see all those elements there. There they all are. And then we're going to make just some true and false statements. Is 11 an element of A? Yes, it is. Is 8 an element of A complement? Here's 8 complement. Yeah, that's true too. Is 5 not an element of A complement? 5 is an element of A complement, so this would be false. We remind ourselves what an empty set means. So an empty set is a set with no elements in it. The symbol for the empty set is the circle with the dash, the line through it. For example, if P is the set of all purple buttons, wait, there's no purple buttons, so P is the empty set. Now we're going to explore the operations of intersection and union. The intersection of 2 sets is the set of all the elements that are both in A and in B. All the elements that are in both A and in B. So for example, if A is the set 1, 2, 3, 4, 5, and B is the set 4, 5, 6, 7, the intersection is the elements that are in both A and B, and that would be 4 and 5, because they are in both sets. Think of the intersection as the overlap of the 2 sets. Where do the sets overlap? And we'll contrast that with the definition of union. The union of 2 sets is the set of all elements that are either in A or in B, or in both. And that's a key part right there. And the symbol for union looks like this. The symbol for intersection looks like that. If A is equal to the set 1, 2, 3, 4, 5, and B is the set 4, 5, 6, 7, A union B, you would take any element that is in either A or B or both. That would include 1, 2, 3, 4, which is in both of them, 5, which is in both of them, 6, and 7. 1, 2, 3, 4, 5, 6, 7. Think of the union as the inclusive umbrella that takes in all the elements that belong to one set with all the elements of one set together with all the elements of the other set. So we're going to explore this on a Venn diagram, but to do this, we're going to need a bigger Venn diagram. We need a Venn diagram that has two sets in it. So I'm going to trade off this Venn diagram for this one. Now, gotta get out here. There we go. All right, look at this one. This one has two sets, A and B. So we'll be able to explore this very well. This is Venn diagram number 2. And in this case, let's put some buttons on in a special way. Let A be the round buttons and B be the set of buttons with 2 holes. So if they're round, they go over here in A. Let's just get them going here. Taking all these nice round ones, and here they go. Got them in A. And there's something special that's going to happen here in a minute, but I'm just starting with finding the round ones. And there's one more round one right there. So A is the set of round buttons, but B is the set of buttons with 2 holes. Let's find buttons with 2 holes. That one's got 2 holes. That one's got 2 holes. And pretty quickly we realize that some of these buttons are both round and have 2 holes. Well, that means they belong in both sets, and that means we have to put them in this region where the 2 sets overlap. It would be that one, that one, that one, and that one. Kind of squish them in. So now everything that's in set A is indeed a round button, and everything that's in set B does indeed have 2 holes, right? Now, that leaves me some other buttons. They have to be somewhere. They're going to have to be outside of both A and B. We never mentioned anything about square buttons with 4 holes. They're going to have to come out here. So that's what this would look like. Now, I'm going to write these numbers on this Venn diagram here, and that's actually going to make it easier in the future to kind of find things. So out here in this outer darkness, we have 5 and 13 and 15 and 3 and 12. In the area where the 2 sets overlap, we have 4 and 1 and 8 and 10. In A itself, we have 2, 14, 7, and 11. And over here in B by itself, we have 6 and 9. Those are all the buttons located. Now, let's explore the idea of intersection. Intersection, again, is the set of all elements that are both in A and B. If you want to think of this another way, imagine the intersection of 2 streets. You have 2 streets crossing each other. The intersection is right there. It's where those 2 streets overlap each other. The intersection in this case would be right in here. It would be the set 4, 1, 8, 10. Okay? In an earlier place, we talked about the symbol for cardinality. When you put an N in front of a set, that's the cardinality of the set. In other words, the number of elements in the set. How many elements are in the set A intersection B? There are 4 of them. Notice the circles in Venn diagram number 2 divide up the diagram into 4 separate regions. 1, 2, 3, 4. 1, 2, 3, 4, looking at either one. All the buttons in A intersection B lie just within one of those regions. Shade that region corresponding to A intersection B. This is where we actually really will eventually get with Venn diagrams, is without having buttons to help us out as manipulatives, we will look at those regions that represent unions and intersections. All right, this has to go away, so we're going to leave this here. List all the elements of A union B. So those are the elements that are in either A or B or both. If this helps, if you think of the word union like a more perfect union, like it says in the Constitution, or like in a labor union, union has the idea of everybody all together. So the union of A and B, all the elements in A or B or both, means just take everybody, everyone that's either in A or in B, or in both. And if I look at that, that would be the following set. I'm copying off my buttons here. I'd have the elements that are kind of in that outer region, the 5, the 13, the 12, the 3, the 15. That's not right. Sorry. They're not included. I was getting too excited about including everyone in my union. They are not in either A or B or both. It's everyone but those. Sorry about that. It's the elements that are either in A or in B or in both. And that would be 14, 2, 7, 11, 4, 1, 8, 10, 6, and 9. All of these buttons here, all of these buttons here, all of these buttons here. And how many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 10, 10. Perfect. Shading the region that's represented by A union B, if that's again everything in A together with everything in B and everything in the intersection 2, that would be all of this area. Union looks like that. Whereas going back a slide, intersection looks like that. Looking back to the answers from question 10 and 13, can you see a mathematical formula that relates N of A, N of B, N of A intersection B, and N of A union B? Let's write down what some of these are. N of A union B, the number of elements in A union B was 10. N of A intersection B, on the previous page, was 4. N of A, that's the total number of buttons in A altogether. That'd be everything here in A. 1, 2, 3, 4, 5, 6, 7, 8. And N of B would be everything in B, and that's 1, 2, 3, 4, 5, 6. Do you see a relationship between these numbers? I will stop talking for just a second. If you would like to pause the video and see if you can see some mathematical formula that connects these numbers, that takes a little bit of effort, but give that a try. So I'm going to pause, and you hit pause, and we'll come back. Okay, we're back. There is more than one way to say this, but here's one way to say it. Notice that if you are interested in the number of elements in the union, that's 10. That happens to be the number of elements in A plus the number of elements in B. 8 plus 6 is 14, minus the number of elements in the intersection. 10 is equal to 8 plus 6 minus 4. And what's going on there is, if you count the union, you might think, oh, union should be easy. I'll just count everything in A and add it to everything in B. But notice if you do that, you end up counting these guys in the intersection twice. So that's why you subtract that element out. List all the elements of B complement. So again, B complement is everything that is in the universal set, but outside of B. So let me try to get an accurate count in there. I have 5, 15, 3, 12, and 13. 5, 15, 3, 12, and 15, 13. Those are definitely outside of B, all out in here. But these buttons in here are also outside of B, and I need to include them as well. 2, 7, 11, and 14. What regions does that represent? All this outer area plus that part of A, which is outside of B. That would look like this. Look good? Now, let's look at or list all the elements that are in A intersection B complement. That means they are both in A, but they're also in the complement of B in the red area, so to speak. Where do we have elements of A that are also outside of B? It would be these guys right here that are in A but outside of B, namely 2, 7, 11, and 14. Where do they live? Well, in A intersection outside of B, that's this area right here. The intersection of A with the complement of B. And we are slowly exploring the idea of creating Venn diagrams, which is really awesome. List the elements of A union B complement. Okay, remember, parentheses means do this first. So if I'm thinking about A union B, that would be all the elements that are in A, all the union elements in B, all the elements that are in both, the union, everyone is all together. We're including everybody, everyone in A, everyone in B, everyone in both. The complement of that would be all the elements that are not in that union. And that would be these guys out here in sort of this outer darkness in the universal set still, but not in either circle. So A union B complement would include the buttons 5, 13, 15, 3, and 12. 5, 15, 3, 13, and 12. Got them all, I think. And where would that be? Again, it's the outer darkness. Outside of both A and B. Not joining in the fun of the union at all. The guys that don't want to be part of the union. There they are. One more set definition is important, and that's the idea of complement of A relative to B. And that's written this way. It's the set of all elements of B that are not in A. For example, let's say we have the set 1, 2, 3, 4, and the set 3, 4, 5, 6, 7. The complement of A relative to B, an easy way to do it is to think of the subtraction like you would have maybe when you first learned about subtraction is take away, start with set B, take away anything that belongs to A. Start with set B, throw away anything that belongs to A. I see a few things that belong to A. 3 and 4 are in B, but they also belong to A. And that leaves me with 5, 6, and 7. Think of B minus A as starting with B and taking away from it any elements that belong to A. All right. We are going to start from scratch. Take all the buttons off the Venn diagram. And this time, let's let A be the black buttons. So I take all my black buttons, put them in A. Like that. And B is going to be the set of square buttons. So I put my square buttons in. Oh, here's another black one. There we go. And we're going to have something similar to what happened before, because some of these buttons are both black and square. So because they're black, they have to be in the A circle. Because they're black, because they're square, they have to be in the B circle. So they would be in the intersection. A is the set of black buttons. B is the set of square buttons. And what about these other guys? Well, they're the ones that this time get to be out here in the universal set, but outside both of these sets, out here in what I like to call the outer darkness. I'm actually going to take a quick peek and make sure nobody slipped underneath. Nope, got them all. Okay. List the elements of B minus A. So again, what B minus A is you look at the set B and take away from it anything that is also an element of set A. That just gives you these 5 buttons right here that are in B but not in A. And that would be 3, the set containing 3, 5. Is that a 6 or a 9? That's a 9. 9, 12, and 15. And the region we're looking at would be right here. How about the elements of A minus B? Well, that would mean start with set A and take away from it anything that belongs to B. That would just leave this area right here that contains 4, 11, and 14. And the region we're looking at is right here. And you can see that that represents the set A, take away the set B. All right, let's keep going. Let's get carried away. Here's a Venn diagram showing 3 sets. We don't have buttons to help with this. That's too many regions. So we'll just take a look at this from here. Here's a Venn diagram showing 3 sets, A, B, and C. Notice that A overlaps with B, B overlaps with C, A overlaps with C. Everything overlaps in every possible way. We'll see this shape many times. Suppose we want to shade the region corresponding to A union B intersection C complement. Let's start thinking about the A union B and the C complement separately. A union B would mean anything that is either in A or B or both, so that's like that. C complement would be everything that's outside of C, so that's that. And the intersection of the two would be those regions that are both shaded gray here and shaded gray here. And the areas that are shaded gray in both places would be this general region right here. I wonder if we can try this on our own. Let's see what we can do. So let's look at let's see if we can shade the region corresponding to A intersection B complement intersection C. Hint, if no parentheses are shown, assume that you work left to right, as if the parentheses were around the first first two terms. Let's just do that. So I'm first going to look at A intersection B complement, and I may need some more color here. So let me bring another pen in. A intersection B complement. B complement would mean everything outside of B, and A would mean A. So we're looking at the elements that are in A, but not in B. So I believe A intersection B complement looks like this. That will be red. Like that. Now we want to intersect that. So the red region intersected with C. Where does the red region overlap C? What are the elements that are in both in the red region and in C? That's going to be these fellows right here. I'm shading in purple. So this would be the purple region. And you'll have lots more opportunities to explore Venn diagrams, but I hope exploring that through the language of manipulatives may have made that just a little bit easier to deal with.